Wait, when is everything going?
Greetings and welcome, friends. When is it going to get going? That's the question on everyone's mind. When will these videos come out? Well, your wait is over, friends. Math is coming at you down the pike, bits per second on the internet flying at your head because you have Wi-Fi, although you don't have a receptor for Wi-Fi in your head. But if it did, you might have a receptor that looked something like this. I don't know. Maybe. So anyways, today we're talking about hyperbolas. That's right, we're kind of in our section about conics. This is the third type of conic we're looking at. And the hyperbola is the set of all points in the plane in which the difference of the distances from two distinct points called foci is constant. So let me talk about what's going on here. So the hyperbola is this curve part, okay? And hyperbola has a bunch of cool stuff going on. It's got a center, right? H comma K sort of thing going on. And then it's got a few other little facts coming at it. Here we go. So here's the center. The orange distance here from the center to what we'll call the vertices is A units. Okay, so there's A units. Here's another A units, and that's a very ugly curly brace, but that's fine. So A units that way, A units this way will give me my vertices, right? The location of each vertex. B units will be this amount, all right? Which that doesn't actually go to a point on the graph, all right? So B units up, B units down gives me these locations, which I use to determine another fact. So for instance, notice I've got this little box drawn around this. All right, and this box is 2a across and 2b high, and it's centered at the same center as our hyperbola. And you draw this box in order to get these little crosshairs, right? Here and here and here and here. And what we do with the corners of the box is we draw these dotted lines through the center and those corners, so those points are collinear. And these lines are called ASYMPTOTES, asymptotes, right? Which you guys, of course, know about asymptotes, right, bro? Yes. You guys remember? No? Maybe a little bit math 3? Yeah. There we go. So, so that's A, that's B. We use those to find the asymptotes, which is implying that our graph actually will infinitely get closer to those asymptotes, but never reach them. All right, so this curve. Yeah, asymptotic high five. Yeah, the fun never ends. So the way you graph this, you draw the asymptotes, you draw the vertices, all right, and then you would draw this in kind of like little quadrants, so to speak, where it leaves the vertex and it approaches that asymptote, but never, ever gets there. Now, the other thing you might realize, hey, this mentioned foci, but just like how foci weren't technically part of the curve in an ellipse, the foci aren't technically part of this either. Let's see, what's a good color? Let's go with, yeah, we'll go with this color. So the foci in this case are actually probably somewhere over here-ish and here-ish, something like that. So this would be like foci 2 and foci 1. And their distance is C units away, all right, from the center. All right, so that's kind of like a bunch of what's going on. And what this is saying, by definition, is that the distance, all right, from the foci to any point, all right, so here's a point, and then here's that the distance between these distances is constant. All right, so if I do the long distance minus the little distance, I get something like this here, this distance remaining. That distance is constant, whichever point I happen to pick on this graph. So if I pick this one, the long distance minus the short distance is the same overall distance at all times. Okay, so that's a bunch of what's going on there. Let's show you what the equation of a hyperbola looks like, at least for our horizontal situation that we've got here. So just like ellipses, you can have a horizontal or vertically oriented hyperbola. And you might notice that the equation is awfully similar, very familiar to our equation for an ellipse. So, here's our equation. It's got the classic x minus h, the y minus k, so you can assume, and you'd be correct in saying that h comma k is our center. It's also got those squared, it's got them in fractions, it's got a squareds and b squareds in the denominators, all sorts of good stuff going on. Very similar to our elliptical experiences there, right? The only difference between this formula and the ellipse, does anyone notice what it is yet? Yeah, this subtraction sign right here. That's the only difference. All right, for the equation anyway. There's some other differences, you know. But for that, that's the only difference. Let's see here. You guys still writing those facts down. So this is a horizontally oriented hyperbola. And the way you actually determine horizontality of this, that's a word, the orientation is determined by whichever fraction is positive. So that's good stuff. So unlike with the ellipse, right, we determined the orientation based off of which denominator was larger. Okay? In the case of hyperbola, that doesn't necessarily work. We might have a larger denominator in the negative fraction. And you'll see with my graph coming up in a moment that can be the case. But it's whichever fraction is positive. And I guess this is actually one way you can kind of make it match the ellipse. Imagine this was a plus sign, and I made this denominator negative. Then I think you would agree that a positive a squared would always be bigger than a negative b squared, like that. So then your kind of elliptical determinations for, right, orientation could follow suit a little bit there. So the center, this is important. How is this equation different from an ellipse? Yeah, this became addition instead of subtraction. So this is actually, in the world of hyperbolas, it literally is the Pythagorean theorem. It's just a squared plus b squared equals c squared. All right, the center is at h comma k. The foci are c units away from your center in the direction of its orientation. The vertices are a units away in the direction of its orientation. It's got a transverse axis, all right, which the transverse axis I'll describe here is this right here. It's called the transverse axis. The conjugate axis is this dimension here. Okay, so the transverse axis is 2a units long. The conjugate axis is 2b units long. So I'll write this as transverse and this as the conjugate axis. So lots of little vocabulary words and terms flying around here. So the transverse axis, right, conjugate axis, like so. And the endpoints of the transverse axis, as you can see, are the vertices. Good, good, good. So, so the transverse axis, the equation is y equals k in the case of a horizontal ellipse. And one more thing I want to tell you is how to find the equations of these asymptotes, all right, which you can actually do with this. I'll tack that on right there. Bam. All right, so the equation of the asymptotes, it's actually, I've got that in point-slope form. Point-slope form is y minus y1 equals m parentheses x minus x1. Which is the equation of a line. You might remember that from Math 1 or Algebra 1 days, whichever it was for you. And point-slope form is convenient because it can be defined based off of the slope and a point. All right, because oftentimes the asymptotes, I'm not going to be familiar with where their y-intercept would happen to be, but I would be familiar with a point that they pass through, specifically the center. All right, they pass through the center there. So that's why I'm going to use h comma k to find those. And then notice the slopes of these, rise over run, it's going up b units and over a units. Or for the other line, it's going down b units and over a units. So for a horizontally oriented hyperbola where it's opening to the sides, all right, this is kind of how I define that, it's opening to the sides, the asymptotes have a slope of plus or minus b over a. And then I plugged in hk for my x1, y1 as the point for those. So that's all that information about that form of a hyperbola. Let me show you a little picture, so to speak, that I drew. Here we are. So here's the a hyperbola that I've drawn. I've got the standard form up here, right? Same thing that you just saw. And I've got some sliders for my h's and k's and the a's, right? So if I slide the h, notice it's actually freaky how those asymptotes shift. Right, so I can actually change the location of that if I want to, all sorts of good stuff. So that's how I change the center, h and k. Now notice what a does. A changes the length of the transverse axis, right, or the length of from the center to a vertex. So I can shrink that down or stretch it out. Actually, having a negative a value doesn't technically make sense because it's getting squared there anyway. But you can see that going on. And what I want to point out is, remember for ellipses, when they were horizontally oriented, they were always wider than they were tall, because that's how ellipses were. In the case of hyperbolas, it's possible to have a hyperbola that this little box is taller than it is wide, even though it's still horizontally oriented. All right? Because the orientation was determined by this sign, not the size of these denominators. Right? And then the value of b changes the length of the conjugate axis. All right, so you can see this little green dotted line is the value of b. This orange dashed line is the value of a. So you can see how those can affect it. And actually, an interesting thing is it's even possible to have a rectangular hyperbola or a square hyperbola, actually, sorry, where the value of a and b are the same, but it's not like a circle. All right, notice it's because the subtract, it doesn't end up having that behavior. So that's just kind of how some of those work. So I just wanted you to get a visual of how that could be. So what A and B end up doing to it and stuff like that. So the only way to get a vertically oriented hyperbola, what do you think I would do if it's not based on the value of A or B? How could I get this to open up and down? What do you suspect is going to do that?
The asymptotes.
It's actually going to be determined. Let's see if I can find my way back. Oh, we've got a fire drill, friends. Bye-bye. No, I can edit them together. And we're back, everybody. Don't worry, no one died in the fire. We all survived due to our ability to solve conic sections. So we were just talking about how would we determine when one is vertically oriented or horizontally oriented, and I'll show you right here. This is an example of a vertically oriented hyperbola. Superbola. Well, how do we tell? Does anyone have any?
Bigger than the x, right?
Oh, I see.
Well, because the y fraction is the positive fraction this time, right? The subtract is with the x in this instance. So, so I'm not going to have you guys write down all these facts, but you can at least write down what the standard form for that guy looks like. I'll fit that down there. Bam, like so. That's good enough. So you've seen this before. This is also found in your book.
Go up a little bit.
Yep. Oh, definitely. Yeah. So so yeah, the key difference to determine that is whichever fraction is positive. All right. So the y fraction is positive, so that's why it's vertical. Question, comment? Yep.
Wait, so the standard form?
The what?
Standard form. Yeah.
Yeah, yeah. Just like how for an ellipse we had vertically and horizontally oriented. That was based off of whichever denominator was larger. In this case, it's whichever fraction is positive. All right. So so yeah. So that's what that looks like for starters. So let's see if we can get a couple examples done today. That'd be good.
Should we write down?
Wait, I want to write down the asymptotes.
All right, yeah, I'll let you. All this stuff is in your text. It's just kind of like switched around horizontal to vertical. The only difference for the asymptotes is it's A over B instead of B over A now. The transverse axis is a horizontal line passing through the x coordinate of the center instead of a vertical line passing through the y coordinate. You know, all that stuff. And then the foci and vertices are similar to ellipses from what we've experienced before. And what's nice, like I said, this one is a squared plus b squared equals c squared to determine the relationships between a, b, and c for all of those distances. So, let's jump into an example quick. Exemple. So, here we are. If I wanted to giraffe the hyperbola, here we go. So this is, fortunately for us, it's in standard form. The first thing we should probably figure out is what's the center? So what is the center? Oh, that actually is a common mistake because in ellipses and circles, the x fraction came first. So yeah, the h is always the opposite of the number with the x. Yep. So 2, -4. So yeah, don't let that throw you off. That's definitely a possibility. Which way do you think this hyperbola is oriented?
Right.
It's vertical because the positive fraction is with the y, right? And just so you know, it's not because this is the bigger denominator, because it technically still could be vertical even if those denominators were flip-flopped. So it's vertical. Let's see, what's the value of a and b?
6 and 5.
A is the square root of the positive fractions denominator, which is 6, and b is the square root of the negative fractions denominator. So once again, untrain your elliptical thinking. It's not based off of whichever is larger. And then to find c, I can just do the straight up a squared plus b squared equals c squared thing, and I could plug in what I know, solve for what I don't. So 6 squared plus 5 squared equals c squared. So I'm going to get, that's an ugly 5, but that's fine. So 36 plus 25 equals c squared. That's what, 61 is equal to c squared? So c is equal to the square root of 61. And I don't believe I can break that down. So I now know a, b, and c. And I know the center, so I can now find the verts. Where's those vertices at? It's going to be a units away from the center in which direction? Let's see. Whoa, I'm getting some laggage. What? Yeah, it's not even writing it. It's so scared. It's like, it's okay, computer. I know I left you in the building during the fire drill. Oh, there we go. There's some vertices. Bam. Man, yeah, it's mad. It's a cranky computer.
You just need to cut me in the throat.
I didn't hear that. So anyways, so which direction am I adding a to? Which coordinate? The y coordinate, because this is vertically oriented. So 2, -4 plus or minus 6 would give me my verts. So those specifically would be 2, 2 and 2, -10. And then my foci, which there are 2 of those still, I'll add and subtract c to the y coordinate. So plus or minus the square root of 61, which is like 7.8 or 7.9-ish, I'm sure, something like that. So now that I have all of that, just like we did for an ellipse, I took the center and I add and subtract a to the direction that it was oriented. So that's why we chose y. And there's only 2 vertices for this one. The endpoints of the conjugate axis, we don't necessarily have to know. So to graph this, let's actually, I'll slide this aside, and I'm going to just get a nice little new sketch with a grid here. Here we go, grid form, square grid. There we are at, bam, bam. I'll hide those points. So let's see. I have to go how far? 2, 2, and 2, -10. And so it looks like something like that would do it. And so here we go. So let's graph it. So the center is at which point? It was at 2, -4. So over 2, down 4. Here's the center. I'm going to move A units up and down from this. So A units above it, put me right here. A units below it, put me right there. And so far, those are the only points on my graph at this moment. Move B units to the right and left from it, which these points are not on the graph. B was the value of 5. So let's see, 5 over would put me at 7 here, and 5 this way would put me at -3. And I'm going to draw the little box. All right. Drawing a box. And the reason I draw this box is that I'm interested in its diagonals, because those are my asymptotes. Right? So far, the only points that are actually on this graph are the purple points. So all of this work is just to figure out where this graph lives. And now that I have the purple points and the asymptotes, I would then draw this, and it's vertically oriented, so that's why it's opening upwards, like so. Then it gets infinitely closer to those asymptotes, but never gets there. And if I wanted the foci, as I said, it was just a little bit less than 8 units away, so I think that was, let's see, was it, yeah, 6, so it would be somewhere here and somewhere here would be where the foci are, so that's C units above and C units below. So those are roughly where the foci are, so that's what a graph would look like. So it looks like we won't have time for our second example, but it's that's fine. It'll be familiar to you based off of your skills with circles and ellipses. But thanks for watching, friends. Have a great day, and avoid fire. Bye-bye.